Looks like we're just about all here, folks. Welcome back, everyone. A few seconds on the clock, and then we'll get started. I think we can officially begin. Welcome back, folks. I hope you had a restful holiday. We weren't working too hard or anything like that. For today's class, we're going to be finishing off section 1.1. We're really just on the last problem there before we move on to the next section. I believe the main takeaway from section 1.1 was really just knowing what row reduction looks like and where you have to do an echelon form type of row reduction or a complete reduced row echelon form, like we mentioned. 1.2 is really the same kind of thing, honestly. 1.1 introduced the course. 1.2 is doing the same kind of things. We're just adding more terminology officially. Like we said, things about pivot positions. We'll finally define exactly what we meant by that instead of just circling at it and pointing at them. And our goal is then we'll finish section 1.1. Assignment 1 will be due a week away from today, since we'll certainly finish that section. Then we'll start working in section 1.2 right after. And the due dates for these are sometimes a little bit in flux. So if we don't finish this section today, that's all right. We'll just move the due date over to a week away from when we finish it on Thursday. And that's pretty much how the whole Moodle course is going to run. All of these will get updated with the solutions that we worked in class the prior day. So if you open up 1.1, then this is the stuff that we wrote out. And each section will be an assignment tied to it directly. If you click on the assignment, it tells you the problems, the page number. If you bought an older edition, you've saved some money, but you'll have to use this document right here, since your problems are definitely different. And it doesn't seem like a bad deal, but if you change just by one problem on some of these, it might go from something we did in class to something totally different, maybe a proof for that type of problem instead. So definitely take a look at these. This is the actual problems out of your book, the right editions. And you don't have to do every single problem. It's just a screenshot. You do the ones that's actually assigned off of this list. And again, just for the sake of fairness, if you're not in the most current edition, you wouldn't see the solutions to the odd problems. So this document is just showing you those odd problem solutions, so you don't feel like you missed out by saving money buying an older edition. So as just some quick reminders, any questions at all, folks, about the Moodle website, the material we did, or otherwise? Okay, well, let's jump back into section 1.1. We already had a holiday across week 1 to week 2, so I felt like it'd be a good idea to, instead of just jumping to the next new problem, let's take a quick look at what we did to get kind of a breather going. So on this example number 4, the problem, well, we added these instructions here. It said, solve the system. But already right here, let me get my things going here. This portion of the problem right here, where we went from the augmented matrix to the system of equations, that's one big, huge takeaway of this section right here. Without being very fluent going left to the right, or from the equations to the augmented matrix, we wouldn't be in very good shape for linear algebra, since we need to know how to do that essentially all the time in this class. But after we did that, we row reduced this. We circled the pivots in orange. We mentioned we're trying to get zeros below and above every single one of those pivots, only because it told us solve that system. We were trying to get what we'll later call a reduced row echelon form, or just simply reduced echelon form is the fast way to say it. Then when we came down to this, its echelon form, we were doing the same thing that we did over here, but our equations are far simpler now. Row 1 is just saying this, x1 is 3, for example. Row 2 is saying x2 is 1, and so on. So that's what solving the system could look like if we're using matrix methods. Definitely, if you try this by hand without a system of, or reduced row echelon form like here, it's a pretty tough problem, I'd say. Well, after getting through that problem, here's the one that we actually ended on. And these look like similar problems, but they're very, very different. If it says solve the system, your pivot circle in orange should look about like this, zeros above and below. But if a question says, just determine if it's consistent or inconsistent, it's a whole entirely different kind of question. They're asking, is there a solution or is there no solutions? Solution existing is consistent. No solutions would mean inconsistent. So here, because of that question, we limited entries only below the pivots. So back here in our final reduced row echelon form, that's why you don't see zero above this pivot, we just need it below. Likewise up here, we had to eliminate this one to get to that format. And finally, we saw right when we got to this, no solution to this system at all. The last row implied a contradiction right there. But that would have been remarkably hard to see just from the ordinary system. There's no way I can tell just looking at those if it's consistent, whether it has a solution or no solution at all. We had to just work it through in the row reduction. Well, any questions or comments at all, folks, with that kind of quick rundown of those last two problems? Okay, well, there's one last example here on the notes, so let's try out this next one, and then we'll move to section 1.2. Just fix those windows there. So here's our last problem for these notes. For this problem, it says, determine the values of h. So our answer is going to be either a number for h or a set of numbers, such that the matrix is the augmented matrix. The moment they said that, it's not a bad idea to do this as an optional thing. Because it's augmented, the stop here is, dashed line here is just going to remind us there's a right-hand side. We're really looking at equations this time. It says augmented matrix consisting of that linear system. And we want to know, well, what h can you put there to make that system be consistent for sure? So that's our whole question. And it really just turns into more row reduction on this. First thing to do to start off is, let's take that system and, well, we want to eliminate the 2 under this pivot of -4. We can definitely make that happen. Say, multiply row 1 by a half, add it to the row below. But you do have options with this. There's lots of ways to get this to the way you want. Instead, you might just swap rows 1 and rows 2 and say that this system is now row equivalent. Let me actually make it come down over here to this new system. We're saying row 1 completely swap with row 2. So I'll use the 2 arrows there. We have 2, -6, -3, and -4, 12, and h. You could put the dash line here if you'd like. I usually only put it in once to start as a reminder, and then at the very end when we're done with the row reduction. So now that we've done that step, you could divide this by 2, but we probably wouldn't want to either since you would have a fraction here. It's good to try to avoid those if we can. But we don't need to make that a 1 to eliminate the -4 down below. That one will be a fast operation. So here's our next row operation. Row 1 is just fine the way it is. We need to eliminate -4 there in row 2. It's all right. Row 2, this arrow is going in one direction, so you can think of it as row 2 gets replaced with the sum of row 2 plus twice row 1. So here I'm just saying double row 1, add it to row 2, and that will absolutely eliminate the -4 down below. Does that make sense to folks so far? Okay. This is only our second-hand row reduction, so if this is going kind of slow, sorry about that. We'll speed it up a little bit more once we get more and more practice, but let's keep on going. Anything in orange, you don't have to write down your homework unless it's helpful. So if you like this stuff, it's a helpful notational log right here that you can write in. If it feels like a distraction, then you're okay to ignore it. But row 1 is going to stay the way it is, so 2, -6. -3. Now we do our operation. So here it says double row 1, that's now a 4. Add it to row 2, and we'll get a result of 0 below. Do it again. This is -12 plus +12 to get a 0. And last time, double this, it's -6 plus h, and we'll get an h -6. Definitely looks weird because the h there and the -6 are not like terms, so we write it in this way. And now that we're at this stage, we have a pivot in this location. We have zeros below. Then when we move to the right, our last pivot is in this spot. We're not trying to get zeros above this pivot position because it's just asking whether it's consistent or not. What value of h would you have to pick? So now that we get to this stage, this probably feels familiar, right? We have row 1 that doesn't say anything too bad. It would say twice x1 minus 6 times x2 is equal to -3. But then in row 2, it says 0 equals h minus 6. Not too different from what we had right here, 0 equals -8. So having a pivot on the far right sometimes is not good, as long as you know that the system was augmented. So that piece of information there was really important for us to analyze this. And we can now say, based on the prior example, because of that entry right here, the system is consistent if and only if h minus 6 takes on a specific value. Anyone recall what this would have to be equal to? Absolutely. Just like in the last system, if we take another peek at it, this system would have been consistent if we had a 0 right there. Last row would have just said 0 equals 0, no problem. You still are going to have a solution in that situation. Here, well, consistency depends, but like you said, it must equal 0 right here. Much like in the last problem. If that's 0, that's okay. You have a consistent system. It would have infinitely many solutions. We still have to solve this, so let's write here h equals 6. I wrote if and only if because now the logic goes both ways. If the system's consistent, h is 6. And vice versa, the only way this system is consistent is you have to pick 6 right up here. There's no other way to make this work out, as weird as that is. What we did, folks, that's really just meant to be an additional question talking about consistent versus inconsistent. Any questions or comments at all, folks, so far? Yeah.
Is it possible to have a 2 or more than one value for the h?
Yeah, I'm going to have some problems. I think it's not quite in this section, but there's going to be other sections where it might have been something like this as an answer. H can't be 6. 6 might be the exceptional value that makes it inconsistent, and it could be consistent for every other value, for example. Or this one might have to think about this one. Yeah, I think that would be really just these two kinds of outcomes. Either you have a specific value or h couldn't be some specific value right here. Does that make sense for that question there? Awesome. All the questions so far, folks? Okay, so I think for the sake of the homework, it probably is not going to look like this. It'll be more similar to the one we saw here, but in general, it could be one or the other. Either one number makes it consistent, or infinitely many different numbers makes it consistent. You're trying to exclude something. Well, let's save up these notes, folks. We've finished the first section of the course. We have several more to get through, but we're definitely well on our way. Like I mentioned, the next section really is just an extension of this one. This introduces the course, section 1.1. And section 1.2 is doing the same kind of topics with just a little bit more definitions on top. Takes it a minute to actually exit out of there. So now 1.1, I'll get these notes uploaded in the morning. The due date for this one's official. And we'll just see what happens with 1.2. I'm not going to try to necessarily race through the sections. But if I felt like I might double assign a section, for example, 1.1 and 1.2 I have on the 23rd, I try to keep the problems a little bit contained so it doesn't feel like you're doing two big, huge assignments all at once. There'll be a couple times a semester where there could be two things assigned at once, but not too often. But let me pull up the notes for 1.2. Let me see if I can fix my windows just a little bit better. Yeah, I think that should work out. So here's our new set of definitions. Lots of reading here, but all this again came directly out of the book. So you shouldn't necessarily feel like you have to take down notes on any of this kind of material. It says here, a rectangular matrix is in echelon form or row echelon form, as long as it has three different properties. So let's take a look at these. And we'll focus on this one to start as we run through the definitions. So first property for echelon form is all non-zero rows are above any row of all zeros. So for example, let's take a look at what they're saying. A row of all zeros would be this one right here. The non-zero rows are these. And for echelon form, there's just a requirement that the non-zero ones are above the zero row. So we have part one satisfied for our initial example right here. Does that make sense, folks, on that first part? Awesome. So next, it says each leading entry of a row is in a column to the right of the leading entry of the row above. That's a mouthful. So there's really a good strategy for reading any mathematical text like this. You have to read it while looking at an example at the same exact time. So let's read through it again. Each leading entry of a row. So let's go to any row, say row 1. This would be the first leading entry. So if we go say, each leading entry of a row is in a column to the right of the leading entry of the row above. Let's go to row 2. The leading entry would be this one, the first non-zero entry. And it says, let's read through it one more time to see if we're in the right setup. Each leading entry of a row is in a column to the right of the leading entry of the row above. So in this row, here's a leading entry. The next row is to the right of the leading entry of the row above. So yeah, we actually do meet that condition. It's just kind of a hard one to read through. Essentially, it just has to have this stair-shaped pattern for part 2 to be confirmed. But that's what we mean by echelon in German, that staircase type pattern that we're seeing here. Last one it says is, all entries in a column below a leading entry are zeros. Let's check it out. Here's the 2 leading entries once again. And if we look below those leading entries, sure enough, everything is 0. So we meet condition 3, and this one is in echelon form already. But it could be even more, say, reduced echelon form or reduced row echelon form. The extra conditions are the leading entry in each non-zero row is a 1. We definitely have that. Those are the leading entries circled, and those are 1s. And it says next, each leading 1 is the only non-zero entry in its column. So in this column, that's the only non-zero entry. Go over here, that's also the only non-zero entry. So this first example meets conditions 1 through 5, and we can say it's in reduced echelon form. Well, that's the rundown of what we're trying to look for. In linear algebra, we want lots and lots of zeros in our matrix. It helps us to find the solutions to systems and so on. And reduced echelon form, this one's good for solving a system. Well, let's take a look at the rest of them. The instructions here were to determine if it's in echelon form or reduced echelon form, like we just found, or potentially neither. Let's try out this weird little game again on this matrix here. But maybe before I get too far, you'll notice that in all these definitions, you keep seeing this word right here, leading entry. It's all over the place. And the book is going to replace that word very, very shortly. Leading entry, just on the very next page of notes, is synonymous with pivot position. So what we're really circling here are the pivot positions, like we mentioned, really on the 1.1 notes as well. But you could call them leading entries as a way to introduce what we're trying to find there. Let's move over to, I guess, this one over here to the right. When you start to analyze these, first look at the rows. Any row that's completely zeroed out has to be on the very bottom. So no issues on this one here. And on this one down below, I like that the 0 row is on the very bottom as well. First thing we'll do is circle this entry right here. Then we go down 1, right 1. Here's the next leading entry. We go down 1, right 1, and this is the next leading entry. Now, we can't get any leading entries or pivot positions going to the right because we cannot go down at all. And if this shape looked a little bit weird, we could fix it by doing row reduction. But the question is more, as the matrix stands right now, is it in echelon form or reduced echelon form? Any volunteers for which one it will be? Echelon, reduced, or neither? I agree. This one's not in reduced, it's just echelon. And what makes this one just echelon is this entry here and this entry there. If those were zeroed out, it would have been in reduced echelon form, but here we'll just call it echelon. Let me make sure I spell that right, echelon form. And just as a reminder, we go to echelon form a lot, it turns out. We're not always trying to solve a system directly, but a lot of times we just want to know, is there a solution to this? And so echelon form is good for checking consistent versus, let me use a comma rather, consistent, comma, non-consistent. So again, one thing that's kind of unusual about linear algebra is the instructions seem to be really important out of nowhere. And the book is very in line with that as well. The way they write the problems is just as big a part of the question itself. So when you go to read the instructions, if they say solve a system, we're doing this. And if anything tells you you're just seeing if it's consistent or not, you want the echelon form. Sometimes getting rid of these two green position here to get to reduced echelon form, it's not necessary for the questions, and sometimes that could be a lot of additional work, sometimes more than twice the work it took you to get to echelon. But that's a couple down. Let's keep on practicing this thing. On this one here, anyone analyze what the situation would be? Is this going to be echelon, reduced, or neither? I agree with you on neither on this one. First thing you want to look at is on row one, this is the leading entry, the pivot position. And now, well, there's no zero down below. It already violates this one. All entries in a column below a leading entry are zero. Well, that entry is not zero, this one right here. So from that position, we have a neither, just like you said. And let me circle this. It's not the only offender, but that's the first thing I probably would have noticed. That makes this one a neither. Does that make sense to folks on the problem with this thing? Okay, row reduction can clean it up, but again, we're only looking at the system as it stands. And then this one looks odd, right? It's got a leading column of all zeros. And just by the way, before we get too far on these, not a bad idea to just specify going this way, we're doing columns. And if you're going this way, you're thinking rows. It seems simple, but honestly, in linear algebra, that's something that can easily get a little bit mixed up on our head. And that could be bad because certain theorems and definitions are very specific about rows versus statements about columns. So we have to be really worry about that to make sure we have it down. But once we get to this first column, it looks worrisome, but there's no problem with a column containing entirely zeros. You'll just start on row one like we always do and go to the first leading entry or pivot position right here. Once we find it, we go down and right. Here's the next leading entry. Then go to down to row three and to the right. This one's going to be the last one. Does that make sense to folks on how we circled off those pivot positions?
You have a question?
Yeah.
So that was written in the algebraic form rather than in.
Oh, yeah, I see what you're saying. Yes.
Would there still be x1 in those equations?
They wouldn't be, yeah. Every equation would have x1 eliminated, but it would be understood that x1 is still part of the geometry of what's going on with the solution set here. Yeah. So it'd be one of those weird cases where a whole variable is eliminated. You might wonder if they could have written a system without that variable, but it still would have to be used in the solution set. Does that make sense with that question there?
Yeah.
Gotcha. Other questions at the moment? Okay, so again, linear algebra, it's all about trying to get loads of zeros in your system, since once you have many zeros, it's easy to read off solutions or tell consistency versus inconsistency. And so this is going to be a good page to come back to, just to determine, or just to practice finding echelon versus reduced echelon, and when we're in this case, neither. Let's go off now to some of the bigger theorems about these things. One thing that's special about reduced echelon form is that this one is unique. So if I give you any matrix, there could be hundreds of different ways to reduce your matrix down to reduced echelon form. In other words, down to something like this, where there's zeros above and below every pivot position. But no matter what steps you take, everybody has a unique reduced final matrix. So that's what's wonderful about that setup. That's not true with echelon form. There are many, many different echelon forms for any given system. In fact, if we look at just this last one right here, oh, I think we forgot to answer this one. This one is in echelon form. If you take a valid row operation on this, you could just multiply row 1 by 5, for example. You'd read 0, 5, 5, 5, 5, and it's still in echelon form. It still give you the same exact information about consistency and inconsistency, but there's now infinitely many different echelon forms for your matrix, but one and only one reduced echelon form when you're going to find the solutions. So that's the uniqueness theorem. Next, pivot position, like we mentioned, this is just the leading entries. We want to find all the pivots that we can possibly find. And any column that contained a pivot position will be called just a pivot column. So that's our new definitions here. And there's a lot going on with this. So I wrote this example too to be pretty similar to one that you'll see in the homework. Sometimes the homework problem requires 3 different parts altogether. I separate this out in part A, B, and C. But let's take a look at your problem, just to show you what I mean by the way these things are sometimes written out. I believe this should be 2 or 3. Okay, so it's problem number 3. This PDF doesn't scale so well. Oh, unless you zoom in. It says reduce the matrices in exercise 3 and 4 to reduce echelon form. Then we'll circle the pivot positions. So this is the second part in the final matrix and in the original matrix. Here's the third part and list the pivot columns. So they want a whole laundry list of different things on this one. Here it's separated out into parts A, B, and C. So we'll be doing the same exact question or same type of question. So it says here, first, here's our matrix A. We'll row reduce to just echelon form. And it says here, do not reduce to reduced echelon form. That's a weird statement there, but if you see that kind of statement, it's because this problem is about telling the difference between each of them. And sometimes you could see some statements like this on exam. Do this specifically. So the question is just about seeing the difference between the 2 forms. And notice we started with A equals on this thing. That's okay. We just designated a whole symbol for that matrix, much like in algebra, you might call X a number 5. But for variables for matrices, usually it's uppercase variables towards the start of the alphabet when we indicate them. So here's an A equals, but when we go to row reduce, I can't write equals at all. We're not going to be writing equal matrices. We'll start doing some of that work in chapter 2. What we're doing is fundamentally changing them. So we use this operator, the row equivalent symbol. So it's going to be a whole new matrix, but our new matrix will have the same exact solution set. Here's how we can start. If you have a weird case where column 1 is completely 0, you might circle a pivot entry right here, like in the prior example. I think for most problems, you're going to find a pivot right exactly here. Then our goal is to eliminate the 2 and the 4, the entries right down below. Our row operations are then going to look about like this. To get rid of that 2, we just multiply row 1 by -2. So row 2 is replaced with row 2 minus 2 times row 1. Let's write that in. First, we copy in row 1. 1, 2, 4, 5. Next, let's do that operation. So -2 times row 1 added to row 2 is going to give us a 0 here. That's going to be -4 plus 4, so 0 here. On this entry, it'll be -8 plus 5, so -3. And this one is going to be -10 plus 4, so -6. Lots of arithmetic in this class. So if you ever notice I put down a number wrong, it'll definitely happen. It's easy to drop a sign or just micro sleep while you're doing arithmetic. Let me know. You can always holler out, hey, Mike, that was a 5 or +6. We'll get it corrected right away. Let's do the same kind of thing multiply row 1 by -4 this time, and we'll replace row 3 with itself minus 4 times row 1. So that's our sum right there, and we'll get 0 to start. This will be -8 plus 5, so -3. -16 plus 4 for a -12. And this will be, I need to remind myself, we're multiplied by -4, so this is -20 plus 2 for a -18. All right, I think we've got our digits. Does that look right to folks so far? Okay, well, now that we've done a row operation, we just want to reassess. Here's our leading entry in row 1, but now this time, we move down and to the right, I'd have to go over here for a leading entry. That's not what we want to do. Our leading entry, if it were right here, that means this one should not have been -3, it should have been a 0. So because there's something constant there, we must do a row operation, a row swap this time. We're going to swap rows 2 and row 3s, and this -3 coming up, we'll put a position right there for our pivot. So that's our next step. And it's not a big step, we're just going to do pretty much this. Row 2, flip or swap with row 3. So first 1, 2, 4, 5 on row 1. Next, here's our operation. We'll put in -3, -12, -18. Or excuse me, starting with the 0 though. 0, -3, -12, -18. Some of you might not have copied that in. If you divided this row by 3 all at the same time, I think that would be terrific. And that's our goal in this class, is to get to the point where you start seeing row operations and where you can take lots of additional shortcuts. But for the moment, we're just doing it methodically, just for the sake of learning it really well. So my last row is going to be 0, 0, -3, -6. At this stage, well, I probably would divide by a -3. Well, you know what, do we have to? Is one thing we should ask ourselves. It says row reduced to echelon form. We did an operation here, but we found when we assessed it, we needed to do a row swipe, or swap is the word I'm looking for. But here we found a pivot in this location, and this location. There's nothing further we can do. Once we have a pivot entry on the last row, we pretty much stop here. We're not eliminating the entries 2, 4, -12 because we're not going for reduced echelon form, just ordinary echelon form. And again, this would be a hint on a real exam. Do not row reduce to reduced echelon form. Sometimes I write in those statements on exams only to help people save time, because you can answer the question right here. There's no reason to do any further row operations at this stage. Well, we got it, folks. That's our echelon form. Any questions about it at the moment? Okay, part B says, circle the pivot positions of the reduced and original matrix. So I'll use different color to make it show. For the original matrix, the pivot positions are here, here, and here. And those entries along this off diagonal here. It didn't have to have those specific pivots. There could have been on the far right column, for example. And, well, this is kind of awkward. I want to also circle it on the reduced matrix. Here are what the pivots look like on the actual reduced matrix itself. The numbers change. They can change wildly, and there's multiple echelon forms. You might have a different answer here. But these pivots are always going to be unique in their position. So the actual positions of where they end up is unique on these matrices. Well, part B is done. We circled the pivot positions, and this is the last part. List the pivot columns of the original matrix, is what it's asking for. Well, the columns are column 1, column 2, and column 3. And you could just say that in ordinary words, columns 1, 2, and 3. But if it says list the pivot columns, I probably would try to do it this way. The pivot columns are it's asking for the original matrix. So we'll go up here and give it this column, 1, 2, 4. We'll be calling these later on column vectors. Next one is 2, 4, 5. And the last one is 454. What linear algebra is going to start doing pretty soon in chapter 1 is work on these kinds of things more often than not, working with column vectors. We have lots of interesting questions we want to answer. We want to know if they're linearly independent, what they span, and all sorts of interesting things. So for the moment, it's not a bad idea to just write them out, just get used to writing these columns. But we did it, folks. That's really just a problem on getting comfortable with reduced echelon form and see how it differs from echelon form. Any questions at all, folks, on getting through this one? Okay, well, let's try out a couple more. Going off to the next page. Here's our theorem 2 next. And it's written in italics because linear algebra is a pretty strange subject compared to other math classes, like, say, a calculus class or an algebra class. Linear algebra is extremely strongly organized in certain definitions and certain theorems. And I'll try to always make a really big deal when we come up to a theorem like this one, which we would consider a core theorem of the course. What I mean by that is, this is a theorem that we'll talk about, my pen just broke, let me grab the other half of it. This is a theorem that we'll talk about, use, and work with in one shape or form in essentially every chapter that we cover in this class, with maybe an exception of chapter 6. That's a very geometric kind of chapter we're working in. So let's take a quick reading of this theorem. But before we get too far on it, let me open up section 1.1 for a problem that we just did. Okay, it says here, a linear system is consistent if and only if, this means the logic runs both ways here, the rightmost column of an augmenting matrix is not a pivot column. So this is all you need to have a consistent linear system. Look at where your pivot columns are, and if there's no pivot column on the far right, you automatically know it's consistent. And echelon form reveals this right away. Let's take a look at 1.1. Just compare that statement. We reduced a couple things, and here's one thing we reduced. We have a pivot column in column 1, column 2, column 3. We ended up with a nice matrix here consisting of only zeros, and we were able to read out the solution. It was definitely consistent. Then we went to another system. On this one, we had a pivot column on column 1, column 2, column 3, and column 4 was also a pivot column. That made this system inconsistent. Well, that's what they're saying right here. If you have a column that looks like this, there's a pivot on the far right entry, much like that -8 here, you'll never have a solution to that system. So that's the first part of the theorem so far. Any questions about it at the moment, folks? Okay, so this theorem tells us a lot. That's the existence part. We also want to know the uniqueness part of the theorem. A good existence theorem should also tell you about uniqueness if it can. Here's what it says next. The linear system is consistent, then the solution set contains either a unique solution. This is when there is no free variables, a concept we're about to introduce. And there will be infinitely many solutions when there is at least one free variable. So if you have at least one free variable, you will have infinitely many solutions. So that's our full theorem altogether. Any questions about it so far? Okay, so it goes along with our trichotomy we had. Let's see if we could pull that up. So in linear algebra, there's only really three things that can happen to any systems. You could have no solution, and when that happens, you have this scenario, a pivot column on the far right. You could have exactly one solution. That means there's no free variables. And what we mean by that is you'll have a pivot corresponding to x1, a pivot corresponding to x2, and a pivot corresponding to x3. All your variables will be accounted for as pivots. That means you have exactly one solution. And we saw that in our work. Here's where we had, we're probably scrolling too much. Let me just go to this one, infinitely many solutions. infinitely many solutions would happen to this system if, say, instead of a -3 here and it's -6, there was a 0 and a 0, it's still consistent, but now there is a free variable. There'd be no pivot tied to x3, and that's what gives it infinitely many solutions. X3 can take on any value now. So that's what we're going to take a look at through this existence uniqueness theorem. I have several systems. We might be able to give all three a try, but I figured we try out a couple and maybe try out this problem next. Let me just get my windows back in order here. Well, any questions at all, folks, before we practice using this theorem here? Okay, well, let's start off with maybe this system. Let me see if I can put in some extra space. It says for the definition, or excuse me, for the instructions, find the general solution. That means we're looking for all possible solutions to this. We'll determine the free variables and the basic variables as we go. We'll define them as we work them. And starting with this one right here, well, we could start with this one, but actually, let's start with this one. This one's kind of special. If you looked at this system here, I would say immediately, no solution. Or you could just say inconsistent. Anyone spot why this system right here would just be automatically inconsistent?
The last row is the 0 and 1.
Exactly. This right here puts a pivot in the far right column, much like right up here where they're specifying. And that's enough to say, like you said, saying 0 equals 1, it's inconsistent. And so no solution immediately on this one. Always it's good to look before you leap with these kinds of problems. So this one's done. Let's now do this one. That one looks like a full official problem. Okay, first thing we have to do to solve this system here by the red dot is we need to transfer it to an augmented matrix. So we'll go, let's be careful. The variables are x1, x2, x3. So it looks like we're not missing any variable. Coefficients will then be 1, -2, -1, 4. Then for row 2, there'll be -2, 4, -5, and a 6. So there it is, folks. That's our augmented matrix. Now we're just going to row reduce this thing. And as the instructions indicate, find the general solution to this, if one exists. Let me just get my space there. There we go. First thing we need to take a look at is where all the pivots are. So here's our first pivot position. And identifying it, that tells us we need to eliminate the -2 down below. It's really not too bad. We'll say it's row equivalent. For our note keeping, we'll write R3 gets replaced with R3 itself plus twice row 1. So that would be our operation. So row 1 gets copied in. 1, -2, -1, and 4. Now we do our operation. So visualize everything here is getting multiplied by 2. Add to the entries directly below. So in column 1, this is going to be 2 minus 2 for a 0. Column 2, this is -4 plus 4 for a 0. This will be -2 minus 5, so -7. And this will be 8 plus 6 for a 14. So we've got it, folks. That's our new matrix. And if we reanalyze the situation on this, here's our first pivot. And we have to go down, right a couple positions to hit our second pivot right here. Oh, sorry, missed that chat. And Prem says, would it be R2 gets replaced with, oh yeah, absolutely. Thanks for spotting that, Prem. I, for some reason, put R3. There isn't 3 rows. There's just 2 rows. Thanks for spotting that. My fix should go like this. R2 here and R2. So row 2 gets replaced with twice row 1 plus R2. Other questions about that so far? Okay, thanks for spotting that, Prem. That was a weird mistake there. The notation is only good if you do it right, and it becomes a big distraction if it starts to get a little bit messed up with those subscripts. Well, that's our new system. But before we get too far, let's also take a look at these instructions. When it said find the general solution, do we want echelon form or reduced echelon form? Any volunteers? How about over Zoom? Do you think we need echelon or reduced echelon?
The normal echelon form.
Good call, because it's asking for, or hang on, I forgot my question here. It wants the general solution, so in this case, it would be a reduced echelon form that we're going for altogether. Does that make sense, folks, on that so far? It's kind of confusing because the words change a little bit from 1.1, but this is the big thing I'd be looking at right there. It wants the solutions, so we need to give reduced echelon form for this process. Let's put here on the notes. Sometimes knowing what the operation is just as important as the whole problem. So we want reduced echelon form, which is just saying we want zeros above and below all the pivots. For this one right here, that's an echelon form, but the moment we take care of this entry, we've got reduced echelon form. So we need to eliminate that -1. Probably I would do that in stages. Let's maybe make this a positive one right here. We need to make that a positive one for reduced echelon form either way, so that's a good step. We'll say that this one is row equivalent to, we're only changing row 2. Row 2 gets replaced with itself. Divide by not 2, let's divide that one by 7. So that should be our operation this time. We'll have 1, -2, -1, 4, and row 1. And now row 2 just looks a little bit nicer. 0, 0. Let's do even better. We need to make that a 1 to get to reduced echelon form. If I'm dividing by 7, that's not going to quite get us there. Let's divide by -7. So that'll be a 1 and then a -2. So reduced echelon form requires that to be a 1, a 0 below, this entry to be a 1, and now we need a 0 above. That will finally take us to reduced echelon form on this process. So we're now eliminating -1 there. Any questions to that stage so far, folks? Okay, well, our operation's not too bad. We're just going to replace row 1 with row 1 and row 2 added together. The symbol would look like this for the note keeping on it. So change row 1 by taking row 1 and adding row 2 to it. So that's our operation. Row 1, excuse me, row 2 is the one that's changing, so I'll put it in as 0, 0, 1 and -2. Then just add these entries above. No changes in the first 2 entries. You only get a change to the right of where your leading entry 1 is. So a lot of times I just start copying 1, -2. There we go. Then I try to remind ourselves what are we doing, just adding the entries together. So 1 plus this -1 will give us a 0. -2 added to the 4 above will give us to a +2. Then this was augmented. We had equality here. So here's our way to denote equality. And last thing I would do is, for every one of these columns, the way we started the matrix was we were pulling coefficients from x1, x2, x3. It's not a bad idea to put this above or just mentally visualize it. These are coefficients now for x1, x2, x3 again. In an equivalent system, it'll have the same solution set. And now we want to determine the free variables and the basic variables. Let me reset my color coding just a little bit. I'll use blue for free variables and green for the basic variables. And the basic variables would be, well, let me actually use a different color here that I can combine with color coding. So here's x1, x2, and x3. And now finally, the basic variables are what you typically have several of these. A basic is going to correspond to where the pivots were. In column 1, we had a pivot, and in column 3. So two basic variables, x1, x3. The free variable is the variable that's not associated with a pivot. But because there's a free variable here that says something about our solution, we know that there's no pivot on the far right column. That's automatically a consistent system because of that. And we cannot have a unique solution any longer. Reason being is there should be no free variables for the solution to be unique. We have this case. The system has infinitely many solutions because there is one free variable x2. And just to be specific, let's say here, x2 is free since it does not, I don't like this word, but it's descriptive, does not correspond, it's just a long word, to a pivot column. So that's the only thing that made x2 free. No pivot in that column. Does that make sense to folks at the moment? Awesome. Now that we're at this stage, we're ready to say what the solution is. This is different from 1.1 because you might have noticed in 1.1, we only looked at an inconsistent system and a system with a unique solution. So we haven't gotten to this kind of process just yet. But really all you're going to do is follow your nose. Write out what row 1 is saying. Row 1 says x1 minus 2x2 plus 0x3 equals 2. I wouldn't you put in 0x3 very often. Probably this would be the last time I would do that. But just as a reminder of where we got it from, the fact that there was a 0 here. Then row 2 would say, well, 0x1, we can eliminate that. Well, 0x2, that's gone. Plus x3, so let's just put in x3, equals -2. So all we've done is we've taken our augmented matrix in reduced row echelon form, transferred it back to a system of equations. And we already have a value for x3, but this is not completely solved just yet. We're about to get to the so-called general solution. All we're really going to do is solve for the basic variables, the one in green, in terms of the free variable, the one in blue. So we need to solve for x1 and x3. Like we said, x1 is the only thing we need to worry about. x3 is already finished. So here is finally our general solution. Okay, now going down the line, start with x1. We'll solve this one and say x1 is going to be equal to, add 2x2 to both sides, and plus 2. 0x3 eliminated, so all I've done is added 2x2 to both sides. So we have a free variable right here. Now, it's a good idea to be methodical with this. We'll see why when we get further in chapter 1. This is really a preview to a technique we'll later on called parametric vector form for our solution. We want to go in order, say something about x1, solve it. Now x2 is free. We just want to write down x2 is free. And going in order like this seems small right now, but I promise you it's going to make a lot of difference later on when we're further on in the course. Next thing we do is we solve for x3. That was already done. x3 equals -2. And this is finally our full general solution to the whole system. It says, well, if you want a solution, x3 has to be -2, or otherwise you don't have a solution. Then put in the value for, let me take another look at this. Yes, put in the value for x2 and do that operation. And you can pick, because it says it's free, any value for x2, 0, 12, pi, and so on. Any value you pick is a solution guaranteed. You just have to put it back up here and do this operation to get your x1. So just for extra description, when you write down x2 is free, what you're really saying is x2 is any real number. If you want to say that a little bit faster, you could just say X2 is in R, the set of all real numbers. Or just say X2 is free, and that's just as great as well. We did, folks. That's wasn't a terrible row reduction, but it had something new, a free variable right in this location. Any questions about getting through this one? Okay, what I want to do next is try out a harder one, but sorry, question first.
So, if you have like a one less row, column,
Oh yeah, less rows than columns.
yeah, so does it mean that you will have a free,
Exactly, yes. There's going to be guaranteed a free variable in that situation, absolutely. So that's one's kind of set up like, well, I guess this one would qualify as well. This one has 1, 2, 3, 4, 5, 6 columns altogether. The problem said we were dealing with the augmented matrix, so the variables would go x1, x2, x3, x4, and x5 on this one. But like you were mentioning, this thing only has 4 rows. At most, there is 4 pivots. But that means at least one free variable will exist in this system, guaranteed. So if you have more columns than rows, there will be a free variable. And there's a bunch of theorems in linear algebra just about that statement. Later on, we'll see statements that say, well, if you have a set of columns that contains more columns than entries per column, rows, that set of columns is linearly dependent just automatically. And that's one of the major things we're going for, independence versus dependence. So the more you can write these things in, think about the variables, what could be free, what's guaranteed to be free, it's going to start helping us out quite a lot in getting through these problems. But we're going for a general solution. This one put it right into an augmented matrix right away for us. And maybe some reduction was done. There's loads of zeros already. So we'll just finish off the reduction on this one and describe the general solution. Any questions so far, folks, or comments at the moment? Okay, I think we have enough time to go for this one. So we'll say that this thing, well, before we just start running down row operations, let's take a look at the pivots. Here's our first pivot positions. Zeros are completely below, so we're set up on column 1. Here's our next pivot position in column 2. But for column 2, it has zeros above and below, nothing to do with that column. Now we have to go down 1 right until we hit the first non-zero entry. Here it is. If there was a non-zero entry anywhere here highlighted in yellow, just do a row swap to put them in the correct order. So on this position, I have a 0 below, and the only non-zero entry is this -8. So we have a one-step row operation, even though the system is quite large on this one. We'll just take care of that -8. Any questions, folks, before we begin? Okay, so here's what our operation would look like. We'll say it's row equivalent to, because of the highlighting, that means we're changing row 1 is replaced with, let's take 8 times row 3, add to row 1. So row 1 plus 8, row 3. But if you look at this really carefully, there's something special about row 3. It only has 1 in this column, the 5th column. Any operation you do on this 5th column will only change this column, not any entries to the left of it or any entries to the right. Does that make sense why to folks at the moment? Awesome. It's really all about those zeros. Multiplying 0 by 8, no change. So effectively, what's going to happen is that's just a 0. It's foregone conclusion at this stage, and nothing else is going to change on the system. Sometimes when people look at these, you might have done this. Just put in a 0 or something like that, and that's not a terrible step to take, because if that was a real exam problem, you just throw a 0 there, you're telling me you know there's only one step to take here, and that resolves it. But let's actually take that step in full, just so that the notes is sensible. We're changing row 1, so I'll start by just writing in rows 2, 3, and 4. Here's row 2, 0, 1, 4, -1, 0, 6. Row 2, or excuse me, 3 is 0, 0, 0, 0, 1, 0, and finally, 4th row is all zeros. And finally, for row 1, that's just gonna be 0, right, where the -8 is highlighted. So it's gonna be 1, 0, -5, 0. Here's our operation. Take 8 times row 3, add it to row 1, 0. So nothing terribly exciting, but it's good to see it done. And the 3 would copy in here, no change. Well, it was augmented, so I'll put that back in. This last example, it's going to be more about specifying the general solution, less about the row operations. But let's analyze for x1, x2, x3, there's a lot of them, x4 and x5. To get the general solution, we need to know exactly which one are pivots and which one are free. Or excuse me, which ones are basic and which ones are going to be free. So we have a basic variable here, here, and then all the way over here at x5. So I think we're using green for those. Let's color code those. So pivot columns are columns 1, 2, 5, and that means basic variables are variables x1, x2, x5. The ones that are free are these ones that do not correspond to any pivot whatsoever. So far linear algebra, all about those pivot columns, pivot entries. That's really what we started doing the very first section 1.1, circling those pivots and doing row reductions based on them. Well, at this stage, we're ready to write out the answer. Any questions at the moment so far? Okay. Now there's a couple ways to do this. On our last example, we just wrote down what equation 1 looked like, put it there. That's a pretty nice step when you're learning this, but it does mean you need to do the additional step of solving for the variable. But here's what you could do if you feel comfortable enough with it. Think of that dashed line as an equal sign. That's what it's meant to denote. And read this equation 1 by saying x1 equals, let's just solve for x1 directly. Row 1 says x1 minus 5x3 equals 3. So let's just take the minus 5x3, add it to both sides of the equation to get plus 5x3, or just 5x3 rather, plus 3. But let me ask the class, does that make sense on that step there? Awesome. So occasionally I'll do it this way, especially if we do a new definition on the problem, but I just want to indicate this is an okay strategy to take if you want to save a little bit of time. Let's keep on going. On x2, there's 2 non-zero constants. So row 2 is saying x2 plus 4x3 minus x4 equals 6. We'll subtract these away, flipping their signs, and add 6. So in other words, x2 is now equal to, from right here, negative 4x3. From over here, it's going to be plus x4. And the right-hand side already had a 6, so we'll just go plus 6 for the right-hand side. So we've got row 2 in. For x3, x4, we'll just write this in. x3 is free. x4 is free. Which, like we said before, that just means x3 and x4, pick any number you want, and they can be independent of each other. x3 could be 5, x4 could be 1,000,000, for example, and that's okay. And last, for x5, well, it would just be x5 equals 0 on this thing. x5 equals 0. So this is a pretty large looking system. It has 5 variables, 4 different equations altogether, but it's also consistent. There was never a pivot on the far right column. We circled the pivot entries to show it. And it'll have infinitely many solutions due to the free variables here. But for what the instructions asked, we did it, folks. This is our general solution. Any questions at all on getting to this result here? Okay, well, we've pretty much done everything we need to do for the notes to be in a good shape for the homework. But I did have one additional question we ought to try, just for the sake of looking at the existence uniqueness theorem once more. So how about we make this our last problem for the day, and then we'll call it a night. That sound right to folks? Okay, so one more. And that last problem, again, it's very much written down for this theorem in mind, so let's solve it while looking at this thing. So for this problem, it says determine the values of both h and k this time, such that the system has, well, there's three parts of this one: no solution, a unique solution, or infinitely many solutions. Now, what it did not say is find the general solution or find the solutions. So we can resolve all three questions right here purely by going to echelon form. Will do the job for us. So let's write that down. We only need echelon form. If we were going for the general solutions, we would have needed the reduced echelon form. Okay, well, we need to get an echelon form, but we first need to get the augmented matrix even just to start this. So here's our system right here. Let's write down that augmented matrix. This one has just two variables, two equations, so it's going to be pretty quick. It goes 1, -3, 1, and then a 2, an h, and a k. Always a good idea to double check your coefficients, make sure we have everything we want. 1, -3, 1, 2, h, and k. I think we're all set. Now we'll go to our echelon form. For this kind of system, two equations, two variables, usually it's just one step to get echelon form. We have a pivot right here. And all we need to eliminate is that 2, and we should be an echelon. So let's see what happens. We're going to row reduce by making row 2 get replaced by itself minus twice row 1. So let's copy in row 1 to start. Once I get this to work. Sometimes Microsoft Word actually slows down and lags a little bit on us. So 1, -3, 1. Let's check the operation. Multiply by -2, add below. So that'd be a 0. This will be h plus 6 on this one. And here, this will be k minus 2. All right, so now we have three different things we want to take a look at. Let's start with this one. No solution. Well, it says determine the values of h and k such that the system has, first, we're going for no solution, and we can use this theorem down below. No solution means it's going to be inconsistent, and they told us it's going to be consistent if and only if there's no pivot right here. That means it's inconsistent if and only if you put a pivot right there, the far rightmost column in your system. So we need to force a pivot in that location to make it have no solution, inconsistent. Does that make sense to folks so far? Okay, so in order to make that happen, let's color code these just so we know what we're looking at. In order for a pivot to be right here, what would you say has to happen to h plus 6? What value should h take right here? Exactly. If we put a 0 there, no pivot in that location. So set h equal to -6. Next, we have to do something over here. Recall, we're trying to force a pivot into this location. And so we need to say k cannot be a specific number. And you want to see what the value would be? Exactly. Anything other than 2, put something non-zero right where it's blue, and that would force it to be a pivot because we just set 0 in that location. So there's only one way to have no solution. Pick anything other than a 2 for k and throw a -6 right here, forcing a 0 in that location. Well, that's our no solution setup on this one. Does that make sense to folks on how we kind of stitched it all together? Awesome. Really, the whole purpose of example 4, these weird problems with h and k, is to look at theorems like this to get the feel for what the theorem is trying to say. Let's go over to the next case. We want a unique solution next time. Add a little bit of room here. So for a unique solution, It says here, we can get a unique solution by not having a pivot in this location to start. So we're trying to eliminate that. And there can't be three variables either. So let's say what we would have to have in this case. So first of all, we need to force a pivot right here where the green field is. If we really want consistent, at least, it's got to be non-zero right there. We can make that happen by going H not equals to -6. Now there's a pivot right there where the green is. And what would you say about this K? Does it matter what the value should be for this location? I agree, it could be anything now. The moment you put a pivot here, and there definitely is, it doesn't matter what H and K is, but we've made it so that's not zero, that's our second pivot. Now these values could be anything. So unique solution, H cannot be -6, and K can be any real number. So that's our second case for a unique solution. Next thing we're trying to get to is what values of H and K must we have for not just consistent, but we want infinitely many solutions next. So that's our next case, infinitely many. I'll just write it in as infinitely many. And the question on the chat was -6 and 2. Let's take a look at that. So -6, that's going to cause that to be a free variable, like Prem suggested. And 2 makes no pivot in this location. So now it's consistent with the free variable. I agree with Prem. That means we would have infinitely many solutions in that case. Does that make sense to folks? Awesome. Thanks for mentioning that. Let's write that in. Let's start with H right here. We want this one not to be a pivot this time. So like Prem said, set H equal to -6. We lost a pivot. So now there's a free variable. If and only if that column still cannot be a pivot or else it's inconsistent. So we'll say, and K must be equal to 2. That gives consistency with the free variable losing this pivot here. Well, that's kind of an interesting run through on this theorem right here. Any questions or comments at the moment, folks, on getting through these? Okay, well, I think we did it, folks. For the problems that you see in the homework, section 1.2, we got through all those problems. And that means when we come back to class on Thursday, you'll see the very next section down below here, section 1.3. But that one is not going to be due on the same date. It'll just be these two sections here and here. Well, any last questions or comments, folks, before we call it a night? Okay, well, have a nice night, everyone. Stay warm, and we'll be back to it on Thursday's class, section 1.3. Yep, have a great one, folks.
Thank you. Have a good night.
Thanks, you too.